All right, today we're going to be looking at topics 2.7 to 2.10, composition, inverses, and logs. Okay, so 2.7, 2.8, 2.9, and 2.10. We're going to have the composition of functions, then the inverse of functions, and then log expressions, and then inverse of exponents, which is log expression. So it's just kind of going deeper on that. All right, composition of functions. So here's how composition of functions works, right? So here you have, wait, sorry, wrong thing. Here you have this function. Take this, f of g of x. Okay, this means that whatever we put into x, then we take the y value of that in the g function, and then that goes into the f function. So here's an example. So let's say g of 1 equals 3. And let's say f is just a quadratic function, so it's going to be y equals x squared. Then when we plug 1 into f of g of 1, first we look at the inside function, g of 1, which is 3. So now we go down, so we can just put that as 3. So now it's just f of 3. So it's asking, what's the value of f when x equals 3? And then we just plug that in here, y equals x squared. 3 squared is 9. So the answer to this, when we're putting x equals 1, is 9. And then for the domain on composition of functions and composite functions in general is going to be X must be in the domain of G. And the reason for that is, let's say X is somewhere that's outside the domain of G, then that would be undefined. And normally we could just write undefined, but since we're doing f of G of X, we can't have f of undefined. That doesn't make sense, right? So X must be in the domain of G, and G of X must also be in the domain of f, because you can't have undefined in composite functions. And composition is not commutative. So what that means is f of g of x doesn't equal g of x, does not equal g of, here, okay, erase the rest of this to make space. F of g of x does not equal g of f of x. Commutative basically just means it's interchangeable. So for example, 7 times 4 equals 4 times 7, right? But that's not how composite functions work, because g of f of x is a completely different thing than f of g of x. It's in g of f of x, which is this right side one, we're going to first take the y value from f of x and then put that into g of x. But on the left-hand side, we do that the inverse, and both of those would often result in different answers. No, you won't need to know the laws by names, just as concepts. But it's just good to know the names when like you're being taught in school, for example, and they use those words, and it's good to know those words, but you won't be tested on them. Decompose. And then here, write a complex function as f of g of x. Okay, so first, h of x equals square root of x plus 3. G of x equals x plus 3. F of u equals root of u. Basically, what's this saying is, what did we do to f of g of x to make it h of x, right? We're taking x plus 3, and then that's on the inside, right? G of x is just x plus 3. So f of x plus 3 equals root x plus 3. So from this, I can tell that what we're doing to this x plus 3 is just taking the root. So f of x, the function f of x equals the square root of x. And we just decompose that function. Here, 2x plus 1, g of x equals 2x plus 1, f of x equals x squared. So f of g of x equals 2x plus 1 squared, because g of x is on the inside, 2x plus 1, so it becomes f of 2x plus 1. And whatever you have on the inside of this function, basically you just plug it in everywhere that x is. Here it's just x squared, so you just plug it in for x, so 2x plus 1 squared, which is what our composite function gives us. So at x equals 2, g of 2 equals 5, because 2x plus 1, right? 2 times 2 plus 1 equals 5. And f of 5 equals 25. So f of g of 5 f of g of 2, sorry. F of g of 2 equals 25. And we can just test that out with our little extra function here, 2x plus 1 squared. So if we have 2, then it's 2 plus 1 equals 5, and then squared is in fact 25. And sometimes you'll be asked to evaluate from a table. So we'll take a look at that too. So g of 3 equals 1, f of 1 equals 3, right? We're trying to find f of g of 3, and they're showing us the steps here. So g of 3, right away, that equals 1, right? We can see on the table. These x values, don't get confused here. These are our x values, like for both f and g. And then these are our y values corresponding for f and corresponding for g. So for example, for the function f of x, when x equals 2, f of x equals 1. When x equals 4, f of x equals 2. And it goes like that. So here, when we're finding f of g of 3, first we have to find what g of 3 is, because we work from the inside out. G of 3 is going to be, okay, x equals 3, g equals 1. So this becomes f of 1. Now we have to look when x equals 1. So x equals 1. We're looking at f this time, equals 3. So our answer for f of g of 3 is going to be 3. And for g of f of 2, it follows a similar process. F of 2, when x equals 2, f equals 1. So, and then it goes g of 1. And then when x equals 1, g equals 4. So this equals 4. Now let's decompose this function. So there's a lot of different ways you could decompose functions if you think about it. There's no one strict way, right? But often you'll be either given one of the two functions so that there is only one strict way, or you'll be given uh, credit for the multiple possible answers. So here for 3x minus 1 to the fourth, right? One possibility this could be is, here, I'm going to cross this out for now. One possibility this could be is for f of g of x. We could have g of x equals 3x. And then f of x, which is on the outside, equals x minus 1 to the power of 4. So this would also work. This is one possibility that we could decompose. But the clear and obvious one here is that g of x just equals 3x minus 1. And f of x equals x to the power of 4. Now we can check here. F of g of x equals 3x minus 1 to the fourth. Let's check that, all right? So first we'll put, and this time we're using these, right? Here, I'll erase these. We're using these two now. So u to the fourth and 3x minus 1. So we're doing f of, and then g of x is just 3x minus 1, so we're going to replace that. And f of u, or it's x, but they're showing u to represent g of x. F of u equals u to the fourth. So it's 3x minus 1, which is the u value, to the power of 4. And that's going to be our check that we decompose correctly. Okay, now here's a couple questions for you guys. 2 questions. First problem, they give you 2 functions, and then they're asking for the they're going to ask for the value that you get from these 2 composite functions of f of g of 4 and g of f of 4. And then they're asking you to write a formula for f of g of x and a formula for g of f of x, and asking if they're equal finally. And over here, we're decomposing this function. So there's, like I said earlier, there's multiple ways you can do this. So if you do it in any way where both of the functions uh, get put together in that composite functions and you get h of x, then you will receive credit. So that would be correct. And there's multiple answers, like I said. And over here, when you're writing a formula, what that really means is, for example, f of g of x. Let's say that f of x, I'm going to use a different example. G of x equals x plus 1, f of x equals x squared. In this example, our formula for this would be x plus 1 squared, because g of x goes on the inside, x plus 1, and f of x equals x squared. So it's going to be x plus 1 squared is the formula for that. So now take a try at these 2 questions and I'll explain it in a couple minutes. All right, I'm going to solve these questions in 3, 2, 1. Okay, so we know that first when we're looking to find the inverse of anything, we swap the x and y. So we did that. Now we have to solve for y. Remember, first so we make it 3x equals y minus 4, and then 3x plus 4 equals y. So this is going to be our inverse function. And let's verify that. Let's plug in this whole thing into where x is here. And if it all simplifies down to x, then it is the right answer. So 3 times x minus 4 over 3 plus 4. So as we can see, the 3's cancel out. The minus 4 and plus 4 cancels out. So this does equal x. So we are correct that the inverse is 3x plus 4. Here, we're trying to find the inverse function of where 3 is. So remember, x comma y is our normal. Our inverse is going to be y comma x. So here, when we're finding the inverse of 3, it's asking us where the y value of 3 is and what the x value is for that. So clearly, that's 2 when y is 3. So this equals 2. Now over here, f of 4, that just equals 4. And the inverse of f of 4, y equals 4, it's still 4. So this is 4. And f is invertible because it has completely different y values for all the x values. So therefore, invertible. All right. Now we're going to look at log expressions. Okay. So logs are basically answering what exponent gives me c. So for example, here it says b of n equals c. Now to find n, we do log b of c. So log base 10. Wait, 1 second. All right. Now, okay, sorry. Sister. Okay. Log, I forgot what I was saying. Log base 10. Oh yeah, so log base 10, this is just common log. So whenever you write just log of, let's say, 100, when you write log and you don't write any base, uh, the base is just going to be 10. So this is basically 10. And with logs, how it works is the base to the power of what equals the actual argument. So 10 to the power of 2 equals 100. So log base 10 to 100 equals 2. Here's some key facts that you need to know for logs. Log b of 1 equals, I'm pretty sure you guys learned this in algebra too, so it's just a quick review. I'm gonna go a little faster. Log b of 1 equals 0 because anything to the power of 0 is 1. And log b of b always equals 1 because anything to the power, let's say like 5 to the power of n or something equals 5. Well, it can't be anything other than 1. It just has to be 5 equals 5, right? So 5, it's going to be to the power of 1. And here, log b to the power of n just equals n. So for example, log 10 to the 10 squared, which is 100. It's asking 10 to the power of what equals 10 squared. So that just equals 2. Because here 2, 2, so it's to the power of. Here's an example of a logarithmic, model, and it's going to be the inverse of exponential models. So here, I'm going to evaluate a couple of these. Log 2 of 32. So again, we put 2 to the what equals 32. If you know your 2's powers, that's going to be x equals 5. Here, 3 to the what equals 1 over 9. Well, clearly it's going 1. It's going over 1, which means it's a negative. Then 3 to the 2 equals 9, so x equals -2. Now, I didn't mention earlier, log, the automatic base is just assumed to be just 10, right? Log 100 equals 2. But for ln, this is called natural log. The base is automatically e, which e is a special number, which has a lot of use cases. And so this ln of e to the 3 is just going to equal 3 because although we can't see it, it's assumed that the base is also e. And by the earlier law we spoke about, it's 3. In the same way, ln of e to the 4 just equals 4. So let's convert this exponent into a log. Remember, we write logs in the version of what to the power of something to the power, something is going to be the base, right? The base to the power of the answer is going to be the argument. So 5 to the power of what equals 125? 5 to the power of 3 equals 125. Here, if we're here, it's easy. The base to the power of 3 equals that. So the base to the power of the answer equals the argument. The argument is basically just this over here. By the way, sorry for not explaining that earlier. Now, a couple of questions for you guys. Evaluate these without a calculator. And then convert between these forms. Rewrite 10 to the -2 as a log. And rewrite log 7 to the 343 as an exponential. I'll give you guys a couple minutes to solve that. All right, I'm gonna solve these in 3, 2, 1. Okay, evaluate without a calculator. First, this log 4 of 64 is asking 4 to the what? So let's set this equal to x. 4 to the x equals 64. And 4 times 4 times 4 equals 64, which is 4 to the power of 3. So x equals 3. By the same process, 5 to the power of x equals 1 over 25. Go a little faster here. Here, x equals -2. Since it's 1 over 5 to 2, 1 over makes it negative. ln of 1, remember our law that anything when the argument is 1 has to be 0, so it's just 0. And we can check that e to the power of 0 equals 1. Okay, rewrite 10 to the -2 equals 0.01 as a log. Okay, so remember our form for logs. It's going to be log. And since 10 is the base, we actually don't have to write the base. We could write it if we wanted to, but there's no harm in not. And then the argument is going to be 0.01 equals -2, which is the exponent. Here, log 7 to 343 equals 3. It's an exponential. It's basically saying 7, which is the base, to the power of the answer, which is 3, equals the argument, which is 343. Okay. All right, final topic of the day now. Inverses of exponential functions. Okay, so the inverses of exponential functions are logs. And we said earlier that to solve for inverses, we just replace x with y, right? So for example, x to the 4 equals y. The inverse of this is going to be y to the 4 equals x, and we have to solve for x. And to do that, we use a log. So it becomes log, wait, sorry, log y x equals 4. And then to solve for x, it's just going to be root 4 y equals x. Oh yeah. And the domain and ranges do swap for these. So like inverses, the domain and range always do swap. So for example, 2 to the x has a domain negative infinity to infinity and has a range from 0 to infinity. But log 2 to the x, 2 of x equals, by the way, I realized like what I did here was a terrible example. It wasn't even the thing. It's supposed to be something to the power of x. So for example, 2 to the power of x equals y. Now I can replace it, so it becomes 2 to the y equals x, which makes, to solve for y, log 2 of x equals y. Okay, so domain and ranges do swap, so that's one thing to note. Here, find the inverse. Okay, so y equals 3 of x. Now let's swap these two. 3 to the y equals x. And then take the log. So log 3 to the power of something equals x. Log 3 to the power of y equals x. And the domain of this original function is going to be negative infinity to infinity. And the range is going to be 0 to infinity. Since 3 to the power of anything, it can't be negative. Now, the domain and range are going to swap for the logarithm. So the domain is going to equal 0 to the infinity. And the range is going to be all real numbers, which I'll also write it like that. Okay. Now, ln e to the x equals ln to the x. It's the same process as earlier. I don't think there's much to go over here. It's just that e instead of log. So now here are the final problems for you guys for today, and then I will solve them right after giving you guys a couple minutes. All right, I'm gonna solve these questions in 3, 2, 1. Okay, find the inverse of f of x equals 5 to the x. So first thing we do is 5 to y equals x. We swap the x and y. Now to put this in a logarithm, we just put log base 5 x equals y. All right. Now our original domain is going to be negative infinity comma infinity, right? Now our original range is going to be 0 comma infinity. R equal e equals. This is for 5 to the x, right? And we do have a horizontal asymptote at x equals 0 equals x equals, no, sorry, it's y equals 0. And our inverse function is just the opposite of all of these. So domain equals 0 comma infinity, range equals negative infinity comma infinity, and then vertical asymptote equals y, no, x equals 0. We just swapped our x value for x and y's for all of it, and we just solved it just like that. Now a bank account is modeled by 1,000 times e to the 0.05 t. So find the inverse of this. Okay, so let's do that. First, we swap the t and y, so y equals 1,000 times e to the 0.05. Sorry, I forgot to swap. Let me erase the y over here. X equals that. So x over 1,000 equals e to the 0.05y. And then it's going to be, to solve for y, now we take the log. So, I mean, the natural log, but it's e, right? ln x over 1,000 equals 0.05 y. And finally, we multiply it by 20 to make this just one. So 20 ln x over 1,000 is our answer for the inverse function. And then how long until the account reaches $2,000? So this is asking for our original one. And it's easier to solve this with our inverse function. With our inverse function, we're looking for when y equals 2,000, right? But with our inverse, we can just plug that in as x. So it becomes 20 times ln of 2,000 over 1,000, which is 2. And we're just going to leave our answer like that because it's no calculator. 28 times ln 2. And then after this time, the count will reach 2,000. And that's going to be our final answer for the day. And with that, we're done with topics 2.7 and 2.10. And I'll see you guys next time.